We come to the most important part of the p-n junction behavior with respect to solar cell operation, a p-n junction under illumination. What happens inside the p-n junction when we shine light on it? In this lecture, we will focus on the depletion region and carrier concentration in a p-n junction under illumination. The learning objectives in this lecture are to understand the impact of illumination on the properties of a p-n junction. How does the illumination influence the charge concentration, and how the illumination influences the thickness of the built-in voltage and width of the depletion region. This schematic picture shows an illuminated p-n junction diode connected through external circuit with a load. There is a current generated by a diode that flows through the load. By changing the resistance of the load, we manipulate the voltage drop at the load and therefore also the power consumed by the load. This p-n junction diode represents a solar cell very well. By changing the resistance of the load, we can manipulate the operational point of a solar cell. We would like to achieve a situation when the product of current and voltage at the load is maximal. In this case, the solar cell delivers maximum power point to the load. We describe this case as the maximum power point at which a solar cell operates. When a p-n junction functions as a solar cell, it can deliver power to the external circuit. You may notice that in this case the current leaves the solar cells from the p-type semiconductor and flows through the external circuit into the n-type semiconductor. So in this case, the electrode attached to the p-type material is the cathode. This is opposite to the situation when a p-n junction diode is in dark and under forward bias voltage. In this case, the dark diode current leaves the diode from the n-type semiconductor, so the electrode attached to the n-type semiconductor is the cathode. There is a schematic circuit representation or symbol of an illuminated p-n junction diode at the bottom of the slide. This is a symbol of an ideal solar cell. One part of the symbol is a p-n junction diode that operates in dark. Its current is labeled ID here. However, there is also a current source that represents a photocurrent generated by the solar cell. Its current is labeled IL. The resulting current flowing through the solar cell and external circuit is a sum of these two currents that, as you can see, oppose each other. Now let's discuss how this photocurrent is generated. Again, we start with a p-n junction at thermal equilibrium. Thermal equilibrium means there is no external perturbation on a p-n junction diode, such as illumination or applied voltage. At thermal equilibrium, the diffusion of electrons and holes across the junction is fully compensated by the drift of electrons and holes across the depletion region. When we illuminate a p-n junction, some of the incident photons are absorbed by a semiconductor material. The absorption of photons results in a generation of extra charge carriers that change the carrier concentration in the junction. To have an idea how many extra charge carriers are created when a p-n junction is illuminated, for example by sunlight, I put some numbers that characterize the carrier concentrations at thermal equilibrium. These are the same numbers we have used in previous videos to characterize a p-n junction. So let's see what happens when we illuminate the p-n junction. The p-n junction is illuminated with photons of different energies. The absorption coefficient of semiconductor materials is dependent on the energy of photons. Usually, the absorption coefficient is high for photons with high energy and low for low energy photons. This means that high-energy photons, shown here as blue photons, are absorbed close to the surface of the semiconductor, while lower-energy photons, such as the red photons shown here, penetrate deeper in the material. For simplicity, let's assume that the p-n junction is illuminated in such a way that there is a uniform generation of electron-hole pairs across the p-n junction. Generation of electron-hole pairs are represented here by the orange explosions. Here are some numbers for you to picture what's going on in a p-n junction under illumination. Let's assume a uniform generation rate through the p-n junction, which is 10 to the power of 20 electron-hole pairs per cubic centimeter per second. We assume that we have a material of good electronic quality. This is reflected by the lifetime of the charge carriers equal to 0.1 milliseconds. We assume that electrons and holes have the same lifetime. From the generation rate and the lifetime of the carriers, we can calculate the concentration of photogenerated electrons and holes. Here we denote the concentration of photogenerated carriers as delta N for electrons and delta P for holes. The concentration of photogenerated carriers under these conditions is 10 to the power of 16 carriers per cubic centimeter. This is also referred to as the injection level. If we take a closer look at these numbers, we can see that the injection level of 10 to the power of 16 is at the same order of magnitude or at a lower order of magnitude than the original concentration of majority carriers. The whole concentration in the p-type region is 10 to the 16, and the electron concentration in the n-type region is 10 to the 18 carriers per cubic centimeter. This means that adding 10 to the 16 more carriers does not significantly alter the concentration of majority carriers. Minority carriers, on the other hand, are at 12 to 14 orders of magnitude below the injection level. This means that adding carriers through illumination will significantly influence the minority carrier concentration while essentially leaving the majority carrier concentration unchanged. You now have a feeling of the charge carrier concentration under illumination that generates electron-hole pairs across the p-n junction uniformly. We will continue our discussion of the depletion region under illumination in the next video.